and the pros and cons of them, how you would decide which of these methods to use if you were given a choice. And then the third thing is just Q&A for reviewing for the final exam. If you have any questions that you specifically want answered in the review session, there is a survey posted on D2L where you can enter your top 3 questions. A couple people have already done that, so we have questions ready to go that I'm planning on answering. So if you have any questions that you want to get answered today in the review question and answer session, go to D2L and put them into the final exam review Q&A survey. It's a survey, so it's on the assessment tabs. I don't know why it's an assessment, but anyways, on assessments survey. All right, so the first thing that I want to talk about is I'm just going to talk about iron, manganese, and sulfur in lakes. And I kind of have a PowerPoint. And at some point, I'm going to ask you to try to draw some profiles. I'm not sure whether that's going to be in the beginning or the middle or the end, but at some point, I'm going to have you draw some profiles because that's what we do in mineralogy. Yeah, I'll check that. All right, so let's start with some lecture here. And hey, Zoom, you want to share my screen? Zoom says only if you click the right button. There we go. All right, so last week we talked about nitrogen and phosphorus. Actually, we talked about phosphorus and then nitrogen. And of course, the reason to focus on nitrogen and phosphorus is because it was they are the most commonly limiting nutrients in lakes. And since a lot of times what people care about lakes in an applied science kind of way is they want to reduce the amount of algae in the lake. It's often people's goal. How can we reduce the amount of algae in a lake? And of course, you could kill the algae, you know, with some sort of herbicide or algicide, but then the algae are going to die and they're going to fall to the bottom of the lake. They're going to decompose. They're going to release all of their nutrients back into the water. And then all of those nutrients are fertilizer from the perspective of the algae, the nitrogen, the phosphorus, you know. So yeah, you could kill all the algae in the lake with some herbicide, but you're never going to kill 100% of them. And the ones that remain, they're going to be like living in nutrient soup afterwards. And then boom, you'll just be back where you were started within a week or two or 3 weeks. You know, sometimes a person wants to kill the algae in a pond for a brief time. And you know, the times when I've seen this done is things like college campuses at the end of summer, you know, when the parents are going to come and drop their kids off and there's like a pond in the middle of campus. And boy, they really want the pond to look good for a week, you know. So yeah, you throw in some copper sulfate, kill all the algae. It's going to take the algae, they grow exponentially, but it's going to take them, you know, days and days or a week or 2 to get back up again. And by then, it's like, okay, the pond can go back to normal. But it's a short term. Anyways, if you're trying to clean up, reduce the amount of phytoplankton in a lake, the most obvious things to focus on are phosphorus, number 1, and nitrogen, number 2. And that's because these are the 2 things that are the most commonly limiting nutrients. Now, in lakes that are eutrophic because of human activity, then typically phosphorus is the limiting nutrient. And it's a pretty rare lake that's not impacted by humans. So basically, phosphorus is the most common limiting nutrient for freshwater lakes. For the ocean and for estuaries, for saline lakes, and lakes that are far from human impact, nitrogen is often, maybe even more often, the limiting nutrient. But one of the things about eutrophic lakes is that if it's limited by both phosphorus and nitrogen, then you're going to get nitrogen fixing cyanobacteria thriving, and they're not limited by nitrogen, but they could be limited by phosphorus. So those are some of the reasons why people focus on nitrogen and phosphorus and nitrogen in that order, and why we started with them. But they are not by any means the only interesting or important elements in lakes. And in fact, the other elements are not unconnected with nitrogen and phosphorus. They're all connected together. They're all in the same water together. And in fact, they're all affected by oxygen. Oxygen influences the redox potential, and the oxygen and the redox potential combine to influence strongly iron, manganese, and sulfur, which interact with each other, and so on. Okay, so try to pull this all together. Let's start by looking at iron, which is simplest, and it's simple, and yeah, and there's lots of information about iron. So, iron. We're going to ask the same essential questions, the basic questions we ask about everything. You know, what is it? What forms does it take? What processes affected? What is its pattern within lakes and among lakes? And what's interesting about it? You know, what else should you know about it? Well, iron is an element on the periodic table of elements. It's an element. And it's important because it is an essential nutrient. Of course, we can't make hemoglobin without iron. And aquatic organisms, animals that have hemoglobin, need iron for that reason. But iron is also an important component of enzymes. It's an important component of the electron transport chain in photosynthesis. It's an important element in some of the components of the electron transport chain in mitochondria. So eukaryotic organisms can't do photosynthesis or aerobic respiration, maybe even any respiration, without iron. You don't need a lot of iron, but with zero iron, you can't live. You can't, the algae can't, zooplankton can't, right? So it is what we define as an essential nutrient, necessary for life. And iron is sometimes the limiting nutrient. It's sometimes the thing, even though not much is needed, but it's sometimes the thing that limits growth. And this is especially true in the ocean, far from land. Most of the iron that enters water, lake water, ocean water, river water, washes in runoff from the land surface. There's almost no iron in the air. There is no gas form of iron, you know, unlike nitrogen, which has a couple of gas forms. Iron doesn't have any. Okay, there's some weird exceptions, but you know, basically there's no gas form. And so if any iron is going to get into a lake, it's going to be dissolving from the rocks in the watershed and washing in the streams. Well, there are large parts of the ocean that are far, far away from land, and therefore far, far away from a source of iron. Now, some exceptions to this obvious rule are the South Atlantic. Africa, the north part of Africa, is desert, and at some times of year there are just enormous dust storms that carry. Yes, Bree, you have a question?
Yeah, this probably sounds really dumb, But when you were talking about how iron appears in the water, I know Lake Superior has a lot of iron ore. Like, would that come off of the rocks, like into the water as well?
Yes.
Okay.
Yeah. So if there's water, if there's iron in the watershed, then that's where the iron comes from that gets into the water. And it comes in from erosion. It doesn't come in directly from the atmosphere. And this is in contrast to nitrogen. So an exception to the general rule that out in the open ocean, you're so far from land that iron is limiting, is the South Atlantic. And that's because the deserts of northern Africa, where there are enormous dust storms and trade winds that go, I'm not sure whether I'm mirror imaging or not here, west to east anyways, carry dust from Africa all the way across the Atlantic Ocean to South America. And there's actually a significant amount of iron carried in that dust, significant from the sense that it fertilizes the ocean. And in fact, if you've ever read The Voyage of the Beagle, Darwin's description of sailing around the world in the Beagle in the 1830s, whenever that was, one of the earliest entries, they're off the coast of South America, and reddish dust is collecting on the sails of the ship and filtering down onto the surface of the deck. And this is dust from Africa. So it's kind of, I don't know how to put it, well known for a long time, not a recent thing. And by limiting nutrient, what we mean is it's the thing in short supply compared to the rate at which it's needed. And the test for that is to add some. And if you add a little bit of iron and you get more phytoplankton growth, then it was limiting. Iron is also important in a way because it forms rusty deposits inside houses, inside pipes, and in streams. Sometimes on the sides of streams, there'll be places where iron-rich water, groundwater has emerged and oxidized, and the iron precipitated, and you can see it. And iron is important in lake sediments because it makes the annual layers visible. And on the right here, we have a sediment core from Lake Zurich. This was in the chapter about, I think, about carbon. And the light layers here are calcium carbonate precipitated, and the dark layers probably contain some iron. Iron, when it is oxidized, is like a rusty red color, rust colored. And iron, when it's reduced, is black. So the banded iron formation rocks of northern Minnesota, the BIFs, the banded iron formation rocks of northern Minnesota, are recording episodes in the history of the Earth when there was oxygen in the atmosphere and the iron precipitates orange, and no oxygen or low oxygen in the atmosphere and the iron precipitates black. And there are banded iron formation, or the iron ore mined in northern Minnesota. And if you're ever on campus, there's some, we got a couple boulders of banded iron formation right near campus. Now, has anybody ever noticed this or had this pointed out in a class when you're on the St. Paul campus? Does anybody know where the BIFs are? There's two places where you can find BIFs right near campus. Getting some no. Okay, they are outside. Okay, there is a boulder in the boulder garden outside the science building itself. And there is also, it's outside the building. And actually there's some beautiful, even better boulders of BIF outside, that's right, the Burger King. Yeah, go look the next time you're there. near campus, go look at the boulders in the front of the Burger King. Yeah, it's kind of amazing. I don't know why they're there. I don't know whose decision that was, but you know, there it is. Okay, another reason that iron is important, apart from making barbs visible and being related to iron mining in Minnesota and the economy of Minnesota, is that iron affects the phosphorus cycle. And we're going to talk about that. Yeah. Okay, so this is what iron is and why it's important. How is iron measured? Well, it's measured with a chemical test. That's all we need to. That's all you need to know for our purposes today. There's a chemical test. If we were to do this, you would take a kit, put in one chemical, put in another, shake it up, wait a couple minutes, turns color. Yeah. There are other ways to do it, but that's the traditional way that limnologists measure it. And that's different from how you would measure conductivity, salinity, like with a meter, right? There's no meter. You could do this. Now, in chemistry lab, you can do fancy chemical equipment to measure it. And maybe hopefully in something like environmental chem, you might talk about that. Okay, what are the units? Micrograms per liter and milligrams per liter. So, parts per billion and parts per million. What kind of range do we see? Well, the two things I would give you as ballpark indicators are ionic iron, so like Fe2, just iron atoms dissolved in water. In water with oxygen in it, neutral pH, 10 parts per billion. Not much, on the order of 10 micrograms per liter. But on the other hand, if you were to measure the total iron in lake water, like take a liter of water and measure all of the iron, not just the ionic iron, you might see 1,000 times as much, like 10 milligrams per liter. How's that possible? Why would it be so much greater? All right, why would the total concentration of iron, total iron, be 1,000 times higher than the ionic iron concentration? Make a guess. And this is going to be the same thing. Really, it's going to be the same reason that we saw for phosphorus. Good guess, good guess, good guess, people. Yeah. And the number one reason is if you were to take a water sample, a liter of water near the surface of a lake, most of the iron is going to be in the organisms. Most of the iron will be in the phytoplankton. Some of it might be attached to other elements, like iron phosphate. But if it's forming a mineral, a chemical precipitate, then it is going to be falling to the bottom. The majority of it will be in the living organisms. So if you go to a lake and you measure the iron ion concentration, it's going to be really, really low. That doesn't mean there isn't a lot of iron in the water. The iron may all be in the organisms. Okay, what forms does iron take? Well, I've mentioned ionic iron. Well, let's look first of all at organic iron. What is the iron doing? Well, there are a lot of proteins that in order to function include one or more iron atoms. Iron is not a part of polypeptides. No, it's not a part of any amino acid, so it's not a part of any pure polypeptide. But a functional protein is often more than just polypeptides, cofactors and other things. And iron is often one of those other things involved in a functional protein. Nitrogenase, the enzyme that fixes nitrogen out of the atmosphere, contains iron. Cytochrome. Cytochromes in the electron transport chain of photosynthesis and respiration, you know, in chloroplasts and mitochondria, contain iron. Hemoglobin contains iron. So, and here's just some molecular structure pictures to show you what these molecules kind of look like. Some are bigger and more complex than others. And here you can see the porphyrin ring of iron suspended by 4 nitrogens in this double bonding ring here. So this is hemoglobin, the heme part of hemoglobin, which is oh so similar to the functional part of chlorophyll, except chlorophyll has magnesium there. Okay, so these are one of the forms that you find iron in lakes is as part of organic molecules. You know, these big categories that limnologists like to use, particulate and dissolved. So in terms of particulate organic nitrogen, you're talking algae, zooplankton, bits of algae, bits of zooplankton, parts of fish, right? And fish, that's particulate organic. And then organic matter can dissolve in water, and proteins can dissolve in water, and other elements, other molecules too. So those would be the dissolved organic iron. In terms of inorganic forms, iron has 2 important oxidation, what do they call these? States. You can have Fe2 or Fe3. Fe3 plus is ferric. Fe2 is ferrous. Ferrous is more reduced. This is important, right? Ferrous is more reduced. Being reduced means gaining electrons. Electrons are negatively charged. So ferrous has a lower positive charge than ferric. Ferric iron is 3 plus. Ferrous iron is 2 plus when it's an ion in the water. And we'll talk about ferric and ferrous iron and how these 2 oh so slightly different forms of iron have completely different places in the iron cycle in a lake. Amazing, one little electron, and it completely changes their behavior. Yeah. What are the mineral forms that you find iron in? The important ones are iron phosphate. And this is important because iron phosphate takes phosphate out of the water. If you've got phosphate and ferric iron, they get together, they form a mineral that precipitates, takes the phosphorus out. Iron oxyhydroxide and stuff related to that is rust. That's what rust is. From a limnologist perspective, rust is not iron oxide, pure iron oxide. It's got water in it too, or at least hydroxyl groups. So I'll call it iron oxyhydroxide to be clear. But if you saw it, you'd probably go, ew, rust. And it's kind of like a rusty, slimy looking, you know, because it's always mixed with water, right, in the water. A slurry, as they say. That's a really important form of iron. And then, of course, iron will bind to sulfur. And it might be, it's usually not literally a 1-to-1 iron to sulfur ratio, but I just drew it as iron sulfide because limnologists usually do. But in certain forms, if it crystallizes and forms a solid, stable structure, this would be pyrite. But even pyrite has different forms. So we're not going to go into the details. We're just going to say iron sulfur, right, at the S, iron sulfide. And that's an important form of inorganic iron. And there is no gas. There's no important gas form of iron. These are the forms. Okay, what are the processes that are important in determining the iron cycle? Well, first of all, precipitation and dissolution, right? Precipitation is ions getting together, forming a mineral that precipitates. If that mineral encounters environmental conditions that make it dissolve, it dissolves. The two ions dissociate and the thing goes back into solution. That's very important in the iron cycle. It's important in the phosphorus cycle too, and it's not really important in the nitrogen cycle. So we talked about it last week, but really only when we talked about phosphorus. Another really important pair of reactions are oxidation and reduction. Iron getting oxidized, iron getting reduced. At the simplest, finest scale, iron is reduced when it gains an electron, when its charge goes down. And iron is oxidized when it loses an electron and its charge goes up. Oxidized iron, Fe3, is ferric iron. Reduced iron, ferrous. Iron is taken up by algae. That's assimilation. Taken up and put into organic molecules, that's assimilation. But when the algae die and decompose, or the zooplankton excrete iron-rich waste and it decomposes, that's the opposite. So assimilation is the iron getting incorporated into organic molecules, and decomposition, or mineralization, is the breaking down of organic molecules, releasing the iron. So it's kind of like the conversion of inorganic iron into organic, and organic iron back to inorganic. Now, the solubility of the iron in the water is another important factor. And the solubility of the iron is determined by the redox potential of the water, the pH of the water, and the form of the iron. So I think we'll talk about these things. So the solubility of the iron is affected by the redox potential of the environment. Is it an oxidizing environment, or is it an anoxic reducing environment? The pH affects the solubility of metals. Acid dissolves metals. So if you got acidic rainwater, you've got acidic soil, then iron and other metals will dissolve. And then, of course, the form. Some minerals dissolve easily, and some minerals do not dissolve easily. Like once formed, they don't break up again. So that affects the iron cycle in lakes. Now I got a couple of diagrams here, and I was working on them last night, trying to improve them, or was that even this morning? Trying to improve them. So hopefully I have improved them and not made them worse. Here's the diagram straight from the textbook. Hopefully the textbook that we're using this year, maybe the one we used 2 years ago. Anyways, so here's the idea. We had a lake, iron comes in from the watershed, in the running water that comes in from the watershed, and some iron will leave a lake, in the outflow. So streams coming in, bring iron in, streams going out, take iron out. And there's typically no significant interchange with the atmosphere. It doesn't evaporate, doesn't come in with the rain. So it's not really, it's such a small amount, we don't even show it in this diagram. Now in this lake, what we've got is in the upper part of the diagram, we have water with oxygen in it. It's an oxic environment, high redox potential. And in the bottom part of the diagram, we have anoxic environment. This could be the hypolimnion with no oxygen in it. This could be the monomolimnion of a meromictic lake. This could be lake sediment, a little bit below the surface. Even in an oligotrophic lake, if you get a little bit below the surface down into the mud, it will be anoxic. So this is kind of shown like the epilimnion and the hypolimnion, but it applies to any kind of situation where you've got an oxic layer, an oxygen-rich layer above an anoxic layer. Could be epilimnion, hypolimnion, could be mixolimnion, monomolimnion, Merrimatic Lake. This could actually represent the surface of the lake sediment in an oligotrophic lake, and this represent deeper in the sediment. The same processes apply. Anytime you've got an oxidizing layer of water above a reducing layer. And you might not think of lake sediment as including water, but lake sediment is full of water. You know, it's probably, well, especially in the upper parts, you know, it might be like 90% water. So it's full of, it's like a sponge of water. Okay, so what do we have going on? Up here where there's oxidizing conditions, iron will bind to phosphate or form aggregates with other metals, or just be iron oxyhydroxide. So it will, under oxidizing conditions, become ferric iron. It will bind to things and sediment. So chemical precipitation refers to the coming together of ions to form a solid. And then the falling through the water is called sedimenting. So we get iron minerals precipitate and sediment down. Down here in a reducing environment, the iron is reduced from ferric to ferrous, and then it no longer sticks to the phosphate. The iron phosphate will dissolve. So now down here in the anoxic part of the lake, you've got ferrous iron. Now, two different things could happen to the ferrous iron, but the one that we're looking at here is the fact that if there's any sulfur around, if there's a lot of sulfur around, the ferrous iron will bind to the sulfur. Sulfur here is in its reduced form, Fe2 minus, and the iron is in its reduced form, which is Fe2 plus. These two will bind to each other and form iron sulfide. Iron sulfide is a mineral that once it forms does not dissolve easily, and it will precipitate to the bottom and just basically stay there. Now, what I've just described is actually basically true for more than just iron. This is the same thing that happens to manganese. You know, manganese in its oxidized form forms minerals and precipitates out. In a reducing environment, it shifts to its reduced form and may bind to sulfur or simply stay in solution. Manganese and iron both form minerals with carbonate, iron carbonates, manganese carbonates, and other things. So this leads to one of the only two, or perhaps it is the only one, joke that I know in limnology. It's a limnology joke. You ready? So we got iron up here, iron oxide. It falls to the bottom, it gets reduced, and then it can diffuse back up again. Where it gets oxidized, forms precipitates and sediments down. And down in this environment, it gets reduced and it dissolves back in the water and it can diffuse back up again. Yes, this is the Ferris wheel.
Stop. I hate it.
Yeah, I had to have a lot of build up for that because it's like a really small joke, but it's like the only joke we have. So there you go. One more time. The Ferris wheel. Yeah, okay. Okay, so what patterns does this cause for iron in lakes? All right, in the epilimnion, here we have a diagram. What we have on the left is dissolved, and here is the scale is going from right to left. On the right-hand side of the diagram in the lighter gray, we have particulate, And this is a normal looking scale. Here's the 0 and it goes up as you go to the right. So up here in this very shallow epilimnion in this diagram, most of the iron will be in a precipitate form. You see there's more iron in particulate, I said that wrong, more iron in a particulate form and only a little bit dissolved. The particulate forms will be primarily organic iron. And up here we see dissolved iron converting into particulate iron by uptake and assimilation by algae that turn it into organic matter, and also the formation of precipitates, which are almost by definition particles. You go down through the metalimnion, and the thing is that algae fall to the bottom and particles fall downward. And so even if there were there probably was more particulate matter here, but it has fallen. And here we are seeing it on its way down. So here we have our highest concentration of particulate iron down here. So when you get to the hypolimnion, which is in this illustration, this cartoon, right, and a reducing environment, you see the highest concentrations of dissolved iron that you see anywhere. Most of the iron is still particulate in minerals and algae, but there is some dissolved and more than any other depth. So why is there so much dissolved iron? Well, what we've got is dissolved iron coming into the water from the sediments. And this particulate is coming down from the epilimnion. So what we're seeing is particulate iron coming down from above and dissolved iron coming up from below. This diagram doesn't show you what's happening in the sediment, but there's really probably two things going on in the sediment. Iron sulfide, which is permanent, doesn't break up again very easily, and iron phosphate, which I'm calling temporary, it dissolves easily. So any of this particulate matter that's iron phosphate hits the sediment, dissolves, diffuses back into the water, contributing to this dissolved stuff. You're also going to have organic iron in the algae that hit the bottom, decompose, it gets released and diffuses back. So that's kind of the pattern that you would expect to see. And this is really a stratified eutrophic lake in summer with a pattern that's driven by the clinograde oxygen curve. Got that? So this is a stratified eutrophic lake in summer. Mammalogists love that, right? Lots of oxygen in the epilimnion, no oxygen in the hypolimnion or very low. And that's a clinograde oxygen curve. That's describing the oxygen concentration, which drives the redox potential of the different layers. Okay, so those are some like big old vocabulary words that we have been practicing using all semester. So just tell me, did that make sense to you, or were you, like, yeah, I know those words: epilimnion, stratified, redox potential, clinograde. Got it? Did you get all four of those, or were you struggling? Give me a thumbs up or a check mark if you were like good with that. If you were like, what? Give me an X. Just give me a sense here of whether that made sense to you. So it looks like most people are saying yes, but not everybody. Okay, well, I'll use these words again, like twice and slowly, so that you can practice using them. All right, and like I said, manganese and the other metals have similar profiles, but we're focusing right now on the iron. All right, what I got here now is I want to show you the iron and manganese concentrations in a lake over time. Now this is basically the hypolimnion, although there is no hypolimnion when it's mixing. So this is just the bottom water. So at 15 to 30 meters of Lake Sammamish near Seattle. So this is the iron and manganese concentration in the bottom water of the lake throughout the year. On the left, these numbers here are the mass, if you can believe that. They took the concentration and multiplied it by the volume of the lake to get the total mass, but whatever. In terms of the curve, it's the same shape as if they just used concentration of iron, which is the open circles, and the manganese, which is the closed or filled in circles. On the right-hand axis, we have the oxygen. And again, they took the oxygen concentration and multiplied it by the total volume of water they're talking about to get mass of oxygen. But it's the same pattern as if they had just left it as concentration. So the vertical axis on the right-hand side is the mass of oxygen, and the oxygen concentration is indicated by the open squares. So here's the oxygen. Okay, so what's the story? January, February, March, April, May, blah, 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 December, January. Slightly more than 1 year. Maybe, yeah, slightly. I think it's slightly more than a year because this would be January. Okay. Oxygen concentration while the lake is mixing is high. The lake stratifies and the oxygen concentration drops pretty rapidly, never quite hitting zero, but pretty low. Then in the fall, November, the lake starts mixing again and the oxygen concentration rises. Okay, let's just stop right here. What can you tell me about this lake? Is this lake monomictic, dimictic, amictic, polymictic? And if it's monomictic, is it warm monomictic or cold monomictic? What term describes the mixing regime of this lake? So everybody make a guess, because, you know, it's free and you learn something from guessing. So what do you think? Monomictic, dimictic, amictic, polymictic, you know, what is the mixing regime of this lake? Let's see, how many answers have we got here? Oh, what am I doing? Oh my God. 1, 2, 3, 4, 5. So just look at the oxygen, right? And these words. So the lake is mixing in February, March, and April, and then it's stratified. Stratified. May, June, July, August, September, October, November. And then it begins mixing again, and it's mixing in December and January. So what term describes this lake? All right, I got a couple of correct answers here. This is a monomictic lake. Well, actually, it's not correct, but you're close. You're close. It's a monomictic lake. It's stratified in the summer and it's mixing the rest of the year. It's not dimictic because there's no ice cover. When you've got ice cover in the winter, it divides, it separates the fall mixing from the spring mixing. And there's no separation here. There's no ice. There's no interruption to the mixing. It just mixes in December, January, February, March, April. So this is a monomictic lake. But it's monomictic because it doesn't freeze in the winter. That makes it warm monomictic. A cold monomictic lake only mixes once a year because it never stratifies. A warm monomictic lake has one mixing period a year because it doesn't freeze. So this is a warm, it may be a little on the chilly side, but in terms of categories, it is a warm monomictic lake. All right, is this lake oligotrophic, mesotrophic, or eutrophic? Oh, how could you tell if it was frozen? They would say it on the diagram. Yeah, so in this diagram, they're just onset of stratification, onset of mixing. There's no mention of ice covering. Also, I mean, personally, I happen to know this lake, and yeah, no, I mean, it's near Seattle. It doesn't freeze over in the winter, but you could just tell from the diagram. Okay, so is this lake oligotrophic, mesotrophic, or eutrophic? All right, everybody just make your best guess. Put it in the chat. Is this lake oligotrophic, mesotrophic, or eutrophic? All right, I think we got two reasonable answers here. I think this lake is obviously not, it's obviously not oligotrophic, right? Because as Bree points out, the oxygen concentration drops in the bottom water. So it's either mesotrophic or eutrophic. Now you might look at this and go, well, it doesn't go all the way to 0, so it's not eutrophic. But this is the average of like the lower 15 meters. And the fact that the iron and the manganese are coming out of solution, coming into solution, dissolving out of the sediment into the water, indicates that at least the sediment surface is anoxic. In this particular diagram, this is not showing the oxygen concentration at the very bottom of the lake. It's showing just the average over the, the lower half of the lake. And the oxygen concentration absolutely drops, but it doesn't drop all the way to 0. But on the other hand, this is like 15 meters, right? So it's pretty clear that at least the sediment surface and the very, very deepest part of the lake have gone anoxic. Therefore, it's eutrophic. The definition of eutrophic, the original definition of eutrophic, was so much nutrient in the lake that the sediment at the bottom water, the very bottom water of the lake, goes anoxic for a significant part of the summer, preventing critters that require oxygen from living in the sediment at the bottom of the lake. Okay, so what's the story that it tells here? A lake mixes in the winter, lots of oxygen. In the bottom water of the lake, no dissolved iron, no dissolved manganese. At the end of April, the lake stratifies. February, March, April, end of April, the lake stratifies. The oxygen concentration in the hypolimnion drops. By the end of May, manganese is starting to rise in concentration in the hypolimnion. The manganese is dissolving out of the sediment into the water. June, July, by the end of July, the iron is starting to dissolve out of the sediment. So the bottom water has gone anoxic by the end of May. The manganese is dissolving almost immediately. The iron is a lot slower to come out of solution, but it does eventually. By mid to late November, the lake starts mixing again. Oxygen concentration in the bottom water rises kind of week after week as the mixing continues. The iron concentration drops, and so does the manganese concentration. It oxidizes, it forms precipitates, and settles out. Are there any questions about what this diagram shows? Can you picture this lake and see these things happening in your mind's eye? Any questions about this? I hope that you can see the relationship between the mixing of the lake, how that affects the oxygen, how that affects the redox potential, and how that affects the iron and the manganese. See, there's a whole long chain of reactions. That's why this is the last week of the class, because we've been building up to stuff like this. Okay. Now we're going to now leave the iron and manganese behind, and we're going to move on to sulfur. Okay, so here's the sulfur diagram. This is from a different textbook by Goldman and Horn that we use sometimes, and it has a stronger chemistry focus because these guys are more sort of physical limnologists. And I tried to make it more clear, and then I just realized that actually I just wanted a whole different diagram. So I'll leave this one behind. There's a whole different diagram. Okay. So, well, okay, this was supposed to build in with stages. I thought I had my, I thought I had my PowerPoint with everything coming in. Okay, well, everything here is here all at once, so let me walk you through it. Okay. So we've got a cycle. Up here we have the oxidizing part of the lake, the oxic. Now this is probably, you could think of this as the epilimnion, and then down here is the epilimnion. Or this might be all of the water if it's an oligotrophic lake, and then the lower part might be just in the mud. In any case, above this kind of dotted line, we've got oxygen in the water and oxidizing conditions. The iron will be present in the form of sulfate. Sulfate can be taken up by algae and converted into organic sulfur. The algae can die, and if they decompose in an environment with oxygen in it, you have aerobic decomposition, and the sulfur would just go back to being sulfate. Now, if that iron were to go into, if this sulfate were to go into an anoxic part of the lake, the bottom water, or into the mud, if it's a reducing environment, then reduction is favored. And reduction means to gain electrons. So if it's in a reducing environment, then it would be energetically favored to give it electrons. If you gave it some electrons, a little bit of energy would be released. And there are bacteria that make their living facilitating this reaction. They essentially take sulfate, and they take electrons, and in a reducing environment, they stick them together. That releases energy, and they live off that energy. They use that energy to make ATP. These bacteria are called SRBs, sulfate-reducing bacteria. Okay, technically, I think that at least some of them are not bacteria. They're actually archaea bacteria. So some people call these SRPs for sulfate-reducing prokaryotes, and some people call them SRMs for sulfate-reducing microbes. But anyways, everybody I know calls them SRBs. So that's the word I used here. So what do? They reduce the sulfate. This releases the oxygen. So you notice there's no oxygen here. So it's an anoxic environment. They are given electrons and releasing their oxygen, and now you've got reduced sulfur. Now, there are photosynthetic sulfur bacteria, like the green sulfur and the purple sulfur bacteria. And they use sulfur instead of water. And in this kind of environment, if there's light and reduced sulfur, they can take it up and convert it into organic sulfur. If you've got organic sulfur down here in a reducing environment and it decomposes, it's not going to be aerobic decomposition, it's going to be anaerobic decomposition, and it's going to release reduced sulfur. So that's what this line represents. And this line here is just showing that, you know, algae from above, in some oxygen-rich environment, regular old algae, can sink to the bottom into the anaerobic environment, and then they're subject to these processes here. Now you've got this reduced sulfur, and if there's any kind of protons roaming around, as there often are in water, protons are positively charged, they are attracted to the negatively charged sulfur, and you get hydrogen sulfide. Now, hydrogen sulfide is a toxic gas. It's dangerous. It's poisonous. It either smells bad or is always kind of co-occurring with other slightly related organic reduced molecules that do stink. So we think of it as being really smelly. Actually, I think that in and of itself, it's odorless, which is part of the reason it's so dangerous. But fortunately, out in nature, you know, you never have just pure sulfur all alone getting reduced. It's mixed in with the mud with other kinds of organic molecules. And there's all kinds, I think, of organic molecules that if they have sulfur in them and the whole thing gets reduced, they form really stinky, smelly, rotten egg smelling kind of molecules. My understanding is that the hydrogen sulfide itself purely is actually odorless, but in nature, you almost never encounter it purely, which is good because it saves lives, honestly. A couple of years ago, this is why you should never go urban caving, urban spelunking. You know, like climbing around in the storm sewers, which people do sometimes. Really dangerous because there can be anaerobic decomposition and gases accumulate. You really should have special training and safety equipment if you're going to do that. And I'm just saying this because I think from time to time we have had a community faculty member who wrote a book on urban spelunking. And I've always, I know people, 2 guys who died in the storm sewers of St. Paul from urban spelunking. Okay, I didn't know them personally, but like guys I know, people I knew them. So I'm just like, in an abundance of caution, I want to point that out to you. Because I don't know, probably Brett thinks that urban spelunking would be fun. Just seeing if I can get Brett to respond.
Does sound pretty cool.
Yeah, it does.
Knowing that.
Be careful. Yeah, I will bear that in mind. Okay, so and then of course, if hydrogen sulfide goes back into an oxidizing environment, oxidation of the sulfur will be favored. And there are bacteria that make their living facilitating this reaction. They live on the mud surface, and you've got maybe at the end of the summer, the mud is reduced and you've got reduced sulfur, and then the lake mixes and it brings oxygen down. The oxidation of the sulfur will happen on its own, but slowly. What the sulfur oxidizing bacteria do is they facilitate that reaction and then they live off the energy that is released. And this is the other, like, extremely small joke in limnology, is that those bacteria are called SOBs, which, you know, might or might not be funny. Okay, so that's the basic cycle, right? In an oxidizing environment, it's sulfate. Put it in a reducing environment, it becomes sulfide. When it's in when it's in sulfide form, it'll form hydrogen sulfide. Here's the connection to the iron cycle. If there is iron in the water, then the hydrogen sulfide will bind to the iron and you will get iron sulfide. This is pyrite or forms of versions of pyrite, precipitates out, doesn't redissolve again very rapidly at all. You know, it takes months before it will redissolve, even if you put it in a reducing environment. On the other hand, if it's a low iron environment, you'll get hydrogen sulfide. So the iron in the water strongly influences the sulfur cycle. But the sulfur also influences the iron cycle because of this connection right here. Now, it's not the absolute concentration of iron, it's really the ratio of iron to sulfur. If the iron to sulfur ratio is high, then you will end up with iron sulfide and very little free iron in the bottom water because the iron gets taken up by the sulfur. If, on the other hand, the iron concentration is low, the iron to sulfate concentration is low, then you will get much greater production of hydrogen sulfide, and the sulfur is available to continue back cycling. I'm going to mention mining in a minute, but I also want to, before I leave this diagram, point out another connection, which is over here. In very saline environments, you can find a relatively high concentration of sulfate in the water, right? In low salinity water, calcium and carbonate are the dominant ions. As the concentration of ions increases, the carbonate reaches its saturation limit first. But the sulfate can continue to increase. The sulfate will form minerals with calcium and sodium. So in very saline waters, you can get precipitation of calcium sulfate and sodium sulfate. Calcium sulfate is gypsum, and sodium sulfate is, in that family of salts that are related to trona and natron and the stuff they make mummies with, anyways. So here's the connection between sulfate and some of the other elements we've talked about, and salinity. Okay, but let's go back to the connection between sulfur and iron. See what we can do here. Okay, so let's take that diagram and put it in a lake. So that's what I did. I took that diagram and I put it in the lake cartoon. So here we have this stuff happening up in the epilimnion and this stuff happening in the hypolimnion. Now let's take the lake and put it in the landscape. I don't know how well this worked, but I thought that I would at least try to show this. So the iron sulfide is buried in the sediment. And I tried to put an arrow in, but I couldn't do it neatly. This organic matter also falls to the sediment too. So in the sediment, the lake sediment, you have sulfur in two forms. You're going to have sulfur bonded to metals, iron sulfide, but also manganese sulfide, copper sulfide, any other metal that's around. And you're going to have organic matter with sulfur in it. Give it a couple of million years and you've got sedimentary rock and fossil fuel. Fossil fuel would be oil. So coal is made out of plants and oil, natural gas are made out of algae. Anyways, fossil fuel. So if you dig up those sedimentary rocks and fossil fuels, and you either burn the fossil fuels, combustion, or smelt the metals, And smelting is like you heat the ore up to drive off the stuff other than the metal. Use a furnace. You heat it super hot and, in brief, drive off the things that are not the metal. Well, doing both of those things to the sedimentary rocks is going to release sulfur dioxide into the atmosphere, because you're taking reduced sulfur from here and oxidizing it. Or else you're taking organic matter with sulfur in it and oxidizing it. So you end up with sulfur dioxide. Now, sulfur dioxide in the atmosphere combines with oxygen and water, it dissolves in raindrops, combines with oxygen, and forms sulfuric acid. Sulfuric acid is a strong acid. If it's dissolved in water, it dissolves in water. And what that means is you get sulfate ions, and 2 protons released to the water. Because this molecule, sulfuric acid, increases the proton concentration of the water, it adds free protons to the water, it is an acid. Now, this step here can happen in the raindrops, and the rain falls as acid rain. Or it could stay in this form and land in the water and dissociate in the water. Either way, what you get is acidification of the water. Iron ore that's in lake sediment, iron ore that's in marine sediment, iron ore that is in sedimentary rocks is often associated with sulfur. That's just its natural state of things. That's how it formed. And metal ores are often associated with sulfur for this reason, because they have formed in anoxic sedimentary environments. Not usually lakes, right? Usually oceans, marine sediments. And this is the reason why there's so much concern about metal mining in northern Minnesota. Metal mining, nickel and copper mining in the Sudbury area north of the Great Lakes, really reduced the area around Sudbury to just like a lunar landscape, completely devoid of life because of the acid rain generated locally by the smelting of the copper and nickel ore. And people are very concerned that even with sort of modern, more conscientious handling, that it's just inevitable that the mining of sulfur-rich oils will release acid. And, you let acid flow into lakes and everything changes. So I wanted to try to show you how, I'm not sure how effective this was, but I wanted to try to show you how the sulfur cycle is connected to the iron cycle and other metals, and how that relates to other environmental issues that you may be aware of. Acid rain through fossil fuel combustion, the sulfide mining issue in northern Minnesota, and, well, of course I like saline lakes, but that's part of that too. I think that's my last slide. No, a little more. Okay. I think this is how I'm gonna wrap up this discussion. This is another figure from Goldman and Horn. This is posted on D2L, except for the figure that I made this morning. And what this is showing in this kind of cartoon diagram is, here we got spring, the lake is mixing. Here we got summer, lake is stratified. Here we have fall, the lake is mixing again. This is a eutrophic lake. So in summer, when it's stratified, the bottom water will go anoxic. Okay, spring, lake is mixing, everything's oxidized, iron, phosphate, precipitate, fine. Stratified, upper water is oxidizing, lower water is reducing. What happens down here? Iron phosphate that's in the sediment separates, dissolves, and dissolves back into the water. Reduced iron that is in the water, if there's any sulfur, will bind to the reduced sulfur, forming iron sulfide. Any sulfate that is in the sediment, whether that was sulfate in and of itself or whether that was sulfate that was in organic matter released by decomposition of the organic matter in the mud, right, is going to get reduced and potentially converted to hydrogen sulfide. Lake mixes in the fall, and this, let's see, phosphate that was released by the dissolution of iron phosphate gets resuspended into the lake. Well, that phosphate that you might have thought was safely buried in the sediment has been redissolved from the sediment and distributed back throughout the water column, where it is available to fertilize the algae. And one of the questions on today's quiz, I believe, was about Lake Shagawa, where they built an expensive water treatment plant to reduce the inflow of phosphate to the lake because phosphorus was the limiting nutrient, but it didn't really work quite as expected. They reduced the supply of new phosphorus to the lake, but phosphorus that was already in the lake keeps cycling, falling to the bottom, carried downward by algae. The algae decompose, but because the bottom water is anoxic, the decomposition leads to soluble phosphorus because the iron releases it. Then when the lake mixes in fall, the phosphorus gets recirculated back into the upper water, taken up by the algae, and you get a whole new algal bloom. So the problem was this kind of constant recycling of the phosphorus from the sediment. This is usually called an internal supply of phosphorus, as opposed to an external supply coming from the watershed. Professor Kalf doesn't like the term internal supply because it's not in the water, it's in the sediment, but you know, whatever, everybody, he can have his pet peeves if he wants, but most people call it an internal supply of phosphorus. And concluding with, here's my last slide. What other kind of interesting things or important things or current research is going on? Iron and manganese are used for what's known as nutrient abatement. They do this in St. Paul water treatment. They do it in lakes. It's a pretty common technique. If you add ferric chloride to water, it will dissolve. Chloride is very water soluble, right? So it will dissolve. The iron will bind to any phosphorus that's in the water, forming iron phosphate, which precipitates out, sediments out. Drinking water pipes often have soldered joints, at least historically, with some lead in the joints. And you don't really want the lead exposed to the water. Typically, there are minerals in the water, and the joints of pipes are prime locations for mineral precipitation to happen. So drinking water, metal drinking water pipes, especially in older buildings, are often not like squeaky clean on the inside. They actually have this sort of gunky kind of precipitate. It's just minerals, and it's a good thing. It coats the inside of the pipes. And the general process is iron and something, Me being any metal, right? It's sort of metal and something, dissolves in the water, and then the metal binds to the phosphorus. And then this forms a precipitate that will coat the pipes. And of course, you know, the problem in Flint, Michigan was shifting to a higher pH water source, a lower pH water source, which dissolved the minerals on the inside of the pipes, revealing the lead joints and thereby releasing lead into the drinking water. And you know, the solution to this is to raise the pH of the drinking water so that the minerals reprecipitate and coat the pipes. But there are cases where people need to do this real fast. So not only will they raise the pH of the water, they'll add phosphorus to the water. I mean, if you can imagine that, I mean, phosphorus is like the limiting nutrient. It's like this powerful pollutant because it's a nutrient. But if you add phosphorus to the water and raise the pH, it'll precipitate. And inside drinking water pipes, that's maybe a good thing. It protects the pipes from dissolving. In other words, it prevents corrosion, but then it specifically could be targeted at lead-containing joints. I hope that was clear. You know, obviously there's a whole big human side to the Flint, Michigan issue, and lots of people get like really excited about blaming people and, you know, all that kind of stuff. But, you know, there are actually some legitimate science involved, which would be the limnology, which is encapsulated right here. Obviously, I'm not particularly interested in like blaming people for things. I'm really more interested in finding solutions. Maybe you could tell that. Anyways, ocean fertilization has been proposed as a way to reduce the greenhouse effect, right? So far open oceans that are limited by iron. The reason that they're iron limited is because they're actually nitrogen limited, whatever. If those algae had a little more iron, they could fix nitrogen from the atmosphere, then they wouldn't be nitrogen limited, and then you'd get an algal bloom. An algal bloom means algal biomass, which means carbon taken out of the air. And then when the algae fall to the bottom of the lake, they take that carbon with them. You don't really need a lot of algae because you've got like a huge surface area of ocean to work with. And the idea is that maybe with a reasonably small amount of iron powder, we could actually take a substantial amount of carbon out of the atmosphere. That sounds pretty good if your whole focus is the greenhouse effect. But on the other hand, what you're saying is, yeah, let's pollute an ultra oligotrophic natural ecosystem. You know, which is obviously, you know, going to harm the open ocean, right? It's changing substantially. So like, I think it's a stupid idea. But anyways, maybe we're desperate. I don't know. Okay, moving on. People have talked about that as a thing to do with iron that involves limnology. I think I've mentioned iron chloride is used in drinking water treatment in at least the St. Paul drinking water supply. Anyways, sulfur, obviously the role of sulfur and its role in metal mining, particularly in northern Minnesota. One of the issues with sulfur and the cycling, which I didn't mention, but when the SRBs are reducing sulfur, they're also anaerobically decomposing organic matter, producing methane. And somehow in the process of reducing sulfur, they methylate mercury. The raising and lowering of water levels seem to be, the rising and falling of water levels seem to be really hard on wild rice. And one of the reasons for that might be the cycling of sulfur. The sulfur gets oxidized when the mud dries out. And then when the mud is flooded, the sulfur gets reduced. And then when it dries out, the sulfur gets oxidized. And there seems to be kind of a sawtooth ratcheting forward of process that occurs in that cycling between wet and dry, oxidize, reduce, which seems to be really hard on the wild rice. And whether it's the sulfur directly or whether it's the connection between the sulfur and other elemental cycles is an area of active research in Minnesota limnology. So I think that's what I want to say about this. I don't have any pictures. In pollution ecology last fall, we talked about this in greater detail, I think, or maybe it was in ecosystem and global, or maybe it was in both. I'm going to talk very much. That's all I'm going to say about it this semester. Okay, that is what I have to say about iron, manganese, sulfur, and how these things all fit together. Reviewing a bit of some of the other stuff we talked about and connecting things to oxygen and redox potential. And I got a celebration symbol from Bree. So let me ask it, do you have any questions? Any questions, anybody? Is this all good? Why don't you give me a little sign if this like made sense to you? Give me a green check mark. Yeah, if you were like, if parts of this were just like, oh my God, I feel worse than I started, give me an X. And if you have a question, please raise your little hand. All right. Well, it is approaching 2:30. So what I'm going to do is I'm going to, I think it's time for us to take our little halftime break. I think what I want to do when I come back is at least start with, and maybe we'll take the whole time, the questions that people have submitted to the review Q&A on D2L. So if you have any questions you want to get answered in the review session, put them in the Q&A, and I will start there with the written questions. And what we're going to do now is we're going to take our coffee break. I'm gonna go get a cup of coffee. I'm gonna have this this chocolate chip muffin here. I'm gonna eat this, yeah, and then I'm gonna come back and answer all your questions. All good? All right, 10-minute break. All right, well, welcome back, everybody. And let's get started here. All right, so here's how the survey looks to me. Now I'm just going to start with, I figure people probably put their top priority question in question 1. So I'm going to start with these. Can we see this? Yes, okay. Will lab 7 be on the final exam or the lab test? Lab 7 was, well, things that are on labs could be either on the lab test or the exam. So that's a good question. Lab 7 was the calculation of heat. And that will be on the exam. Calculation of the Simpson's diversity index calculation. That's an example of a thing that, well, I mean, we did it in a lab, but we also talked about it in a lecture. It could go either way. Calculation of the weighted average TSI, trophic state index. That's more likely to be on the lab test. I did not write a new lab test study guide because I didn't have time. I just didn't have time. But hopefully you can guess. It's basically the same as it's really the same as the study, it's the same as the study guide for the first lab test, but in the second set of labs, we also did calculate the weighted average TSI, which we hadn't done before, so it's not listed on the first study guide. But I think that a lot of people scored less than 100% on the first lab test. And all of those same things are still important. So my plan is to have the lab test be really very similar to the first lab test. And see, you know, hopefully all the people who got those questions right the first time will get them right again. And some of the people who got them right the first time will get them right this time. Okay, they won't be exactly the same numbers, but you know, exactly the same types of questions. So that's what I would have to say about the lab test. I'm optimistic that people will raise their scores, you know. So it's not rocket science, it is statistics. So that's a long-winded answer to the question about lab 7. Why is there so much effort to decrease phosphorus in surface waters? Why not nitrogen? I think there's 3 main reasons why the focus is on phosphorus instead of nitrogen. First of all, nitrogen fixing bacteria can ruin your phosphorus reduction, your nitrogen reduction strategy. Second of all, right, because you could reduce the nitrogen and then what? You get blue-green algae, you don't care that you reduced it, they're gonna grow anyways, if you know what I mean. Second, technically speaking, in terms of the chemistry and the industrial equipment involved, it's easier to reduce phosphorus. I don't know why that is, but they just say that if you're going to design a nutrient removal method, it's easier to remove phosphorus. So that's the second reason. It's just practical, logistical. And the third reason is, that phosphorus is more often already the limiting nutrient. And there's less of it in the water to remove. I'm not sure. That's kind of a third big reason. I hope does that answer that question? Any more questions about it? If you have any more questions about the question, just raise your hand. Even if it wasn't your question to start with, if you want me to explain more about that topic. Okay, I'm going to move on to the next topic. Mount water has maximum density of 4. Which of the following does this cause? None of these. None of them. 4-degree maximum doesn't cause stratification. The ocean is seawater. Seawater doesn't have a 4-degree maximum. It stratifies. Ice floats. Yeah, that has nothing to do with the 4 degrees. Heat of vaporization, nothing to do with the 4 degrees. High viscosity, nothing to do with the 4-degree max. High specific heat, nothing to do with the 4-degree max. High melting point, nothing to do with the 4. Yeah, really, it doesn't have anything to do with any of these. The reason that pure water has a 4-degree max is because water is able to be closer together as a liquid. The water molecules are closer together when they are a liquid than they are when it is a solid. And they have to like rearrange and expand in between getting down towards the ice stage. That obviously is something that really only applies. I didn't really describe that very accurately, but the point is it really only applies to that temperature of liquid water that's near the temperature of freezing. Things like heat of vaporization, viscosity, specific heat, those don't really have any particular connection to that narrow little temperature band. And of course, ice floats because it's way less dense than liquid water. And lakes stratify, that's because warmer water is less dense than colder water. Yeah. Any questions about this topic? I know that some of you were taught or told that the 4-degree max was the reason for this or that or the other thing. I do know somehow that some of you were probably told or taught in something incorrect. And I know it is much harder to unlearn something than it is to learn it. But this is truth, so you should learn it. Okay, other questions? Anything about this? Yeah. All right. Can we do a Simpsons D example? Yeah, let's just do a Simpsons D example. There are different versions of Simpsons diversity index. It's been around a long time and it's really useful, and it is used in a variety of different sub-disciplines of biology. We use 1 minus the sum of all piece of I squared from I equals 0 to n. So piece of I is equal to the number of cells of your species, or the number of individuals of your species, divided by the total number of individuals. So in other words, it's the percent or the proportion of the population that belongs to that species. And you take that number and you square it, and you add all of those up. And that gives you the probability that 2 individuals chosen at random belong to the same species. And then we subtract that from 1 because it's illogical. I mean, it's counterintuitive. It's the opposite of what you would expect. In a high diversity community, we expect the 2 individuals picked at random, this one and that one, this one and that one, you know, whatever. In a high diversity community, we would expect 2 individuals picked at random would be different. In a low diversity community, 2 individuals picked at random might belong to the same species. The less diverse the community, the higher that probability. It's a number between 0 and 1, between 0 and 100%. And the reason that we do the 1 minus the sum is because this way, in a low diversity community, Simpson's diversity index is a small number, a low number. And in a high diversity community, Simpson's index is a high number. Simpson originally formulated it just as this. Ecologists usually use this version, which is a modification. If you are in a very small community, such that taking 1 individual seriously changes the probability of what you're going to pick for the next one, then you wouldn't use this. You would use p times p minus 1 because you've reduced the population by 1, or something like that. But we don't do that because we're working with like real communities with big populations. So that was just for those people who use that variation, which maybe you learned in some other class, I'm not sure. Okay, so an example. Let's say that we've got a community of diatoms. Let's say there's some Asterianella fernosa, some Fragillaria crotonensis, which I'm just reading in this way, maybe some Cyclotella maniginiana. These are species. And here we have the number of cells. And let's say that the number of cells that we saw were like 50 and 25 and 25. And I picked these numbers because they're really easy to work with. You know what I'm going to do? I'm going to make this easier, sorry. There you go. Is that easier? Is that better?
Thank you. I was about to say something. I'm like, I can't see.
Yeah, I could sense that. Yeah. Okay, so let's say you got 50 of this and 25 of this and 25 of that. And I picked these numbers because they all add up to 100. So the calculation is going to be easy. So calculating piece of I, this is 50 divided by 100. equals 0.5. This is 25 over 100. And this is 25 over 100. Like I said, it's pretty easy. Or, you know, it's even easier. I like to use fractions. 50% is 1/2. That's a quarter. And that's a quarter. Piece of I squared, right? If you've got a community and half of the cells are Asterianella formosa, and you just pick one cell at random, there's a 50-50 chance that cell will be Asterianella formosa, because half the cells are. So I got my finger on the microscope slide, and let's say I picked another sample at random. I picked another cell at random. What are the chances this one is Asterianella formosa? Well, 50-50. Half the cells are Asterianella formosa, so there's a 50% chance that that's what that is. So I had half the time this was Asterianella formosa, 50% chance. Of the times that that was Asterianella formosa, half of them, this was also Asterianella formosa. So a half of a half is a quarter. It's a half times a half. So the chance that the both of them are the same species, Asterianella formosa, is 50% times 50%. In other words, 0.5 squared. So this would be 0.25 or 1/2 squared. This would be 0.25 squared, which is a 16th. This would be 0.25 squared, that's another 16th. And if you add these all up together, 2/16 is 1/8, quarter is 2/8. So in other words, 3/8. Now I can't square 0.25 in my head. I think it's 0.625, but I would want to check that. Yeah, 0.0625. There we go. So this is 0.0625. 0.0625. That's 1.25. 0.125. That's 0.375. So 3/8. 3 divided by 8, 0.375. So that's the sum of these numbers. And then 1 minus pi squared is going to be 5/8 or 0.625. So that's the answer. Okay, so there's an example of calculation of Simpson's diversity index. What's the species richness for this community here? Anybody happen to know? Species richness? Yep, 3. 3 species, and that's what species richness means. How many species? Yeah. Now, I have to say that Simpson's diversity index is not the most commonly used diversity index by professional ecologists writing papers. It's more common to use the Shannon-Weiner index, which is like the number times the logarithm of the number, or the proportion times the logarithm. But it doesn't have the same kind of intuitive, makes sense feeling to it. So that's why we use this one and why we use it in this form. It is widely known, widely used, and in part because it makes sense. A community that's more diverse is going to have a higher number, less diverse, lower number. All right, any questions about this? All right, and if you do have a question, but you're just a little slow moving, you know, you can always raise your hand and we'll go back to. Okay, what two things, according to Calf, are responsible for seasonal variations in redox potential? He talks about the things that determine the momentary balance, the balance between, you know, on short time scales and stuff, and that's photosynthesis and respiration. So the redox potential goes up and down with the oxygen concentration. Other things affect the redox potential too, like, you know, other elements that are in the water that might be looking to get reduced or looking to get oxidized, things that are looking to get rid of electrons or things that are looking to pick up electrons. So all of those other chemicals that are in there for different forms of nitrogen, different forms of iron, different forms of sulfur. But in terms of like what's making it go up and down, you know, daily or weekly or even seasonally, it's really oxygen, photosynthesis and respiration. Right. All right, there are other things that affect it, you know, particularly reduction and oxidation reactions. Those would be like the next two. All right, why are there few diatoms per milliliter in the water Lake Phalen in mid-June than they were in mid-May? In other words, what is it that causes the end of the spring diatom bloom? There are three causes for the end of a spring diatom bloom. And it really seems like this is the reason why spring diatom blooms so reliably end, because if it's not one thing, it's the other. And those three things are an increase in population of the zooplankton that eat diatoms. Diatoms are crunchy and oily, you know, as long as they're not like big heavy things, they're pretty easy for things to eat. And so increase in the population of zooplankton is a big reason. And one of the reasons we know that is when people have done exclosure experiments, you know, excluding the zooplankton. There was that study in Memphremagog in Quebec, and where they had, it was a benthic experiment, but when they excluded the algae eaters, the diatom bloom went on and on and on. Second, if you're talking about plankton, lakes stratify. And the stratification of a lake means a thin mixed layer. When a lake is mixing, the whole lake is mixed, if it's a holomictic lake. Well, when a lake is stratified, it's only the epilymnion. And when lakes stratify, the epilymnion is thin, is shallow in the beginning of summer, and it gradually gets deeper and deeper over the course of the summer. Look at some of these isopleth diagrams we've looked at, and you can see that over the course of the summer, whichever direction we're going, over the course of the summer, the epilymnion gets thicker and thicker and thicker. People who have gone swimming in June, if you think about it, June is the time of year when you can be swimming and it's warm, the water's warm, but if you stop and you start treading water, your feet get cold. That's a sign that the epilymnion is only like, 4 or 5 feet thick. That's an early summer situation. Why does it matter to a diatom? Well, diatoms sink. They sink on average approximately about a meter a day. If the epilymnion is only 3 feet deep, then over the course of one day, you would expect something like 90, a half, I don't know, all the diatoms to sink out of it. If the epilymnion is 1 meter deep and it's calm overnight, so there's not a lot of turbulence, then really, even the diatoms at the top of the epilymnion have a high chance of sinking all the way out of the epilymnion by the end of the night. At least a 50-50 chance. So the increased loss rate from the population due to the sinking of the diatoms is a big reason in some places that could cause the diatom bloom to end. The third reason is silica. Silica diffuses into a lake from the bottom, from the sediments gradually. It washes in from the watershed. And in the springtime, the diatoms suck up all that silica and use it to make frustules, make new valves. But once they have used up all the silica in the water and all of the silica that they have stored inside, which may be enough for one more cell division, they can't divide anymore. And really, there are no diatoms. Okay, there's like one weird exception, which might possibly be true, but there are no diatoms that don't have valves. There are no diatoms without silica valves. They all have them. They can't live without it for some reason. They don't live without it. So therefore, if they run out of silica, they can't reproduce anymore. And then their natural loss rate will drive their population down. So I think those are three big reasons why the diatom bloom ends in the spring. Any questions about that? Was that clear? Makes sense? Okay. All right, which statistical test do you use when the independent variable and the dependent variable are both categorical? All right, everybody needs to know the answer to this question. Many of you already do. What is the answer? Independent variable and dependent variable are both categorical. So give me a chat. Tell me what it is. Yep, chi-square, the chi-square test. Yeah, some of you are still typing, but you're typing the right thing. You're typing chi-squared, right? What tests do you know? Chi-squared, rank sum, t-test, regression. I guess if regression is used as a test. Which molecule is the main source of the oxygen that plants incorporate into sugar and other carbohydrates? In photosynthesis, water is split, and the protons combine with carbon dioxide, make sugar. So where does the oxygen come from? Carbon dioxide. The oxygen in the water is released as oxygen gas after the water is split in photosynthesis. So the answer is carbon dioxide. Any questions? All right, let's move on to people's second question. Consider a lake in which only 20% of the surface light reaches a depth of 1 meter. What is the extinction coefficient for this lake? All right, what I want to do is, I guess I'm just gonna, shall I just write this answer on the board? And we'll talk our way through it. Consider a lake in which only 20% surface light reaches a depth of 1 meter. What is the extinction coefficient? All right, let's start with a cartoon, right? So this is
Can you make your screen bigger, Virginia?
this is light and this is depth. Okay, so this is light and this is depth, and we know that light decays exponentially, or decreases exponentially with depth. Something like that. You can see that. Some kind of exponential, right? And the formula for this line is the initial amount of light times e to the negative kz. Or the alternative version of that would be lambda to the z where lambda is equal to e to the negative k. Right? So here's exponential to k. It's exponential to k because this, that's a little cursive k. You can't quite read the scribble. This is a negative number. Now either k is a negative number or there's a negative sign here. But either way, the thing that's multiplying z, depth, this has got to be negative. Now, alternatively, you could write it like this and just use lambda in place of the e to the negative k. And then in this case, lambda is what fraction of the light gets through 1 meter of water. Every meter of water is going to cut out the same amount of light, the same percent of the light. And each meter of light is going to allow through, transmit, the same fraction of light. So lambda is the fraction of light transmitted by each meter. So we got some equations here. And the information that we're given is no longer visible to me, but 20% was in it, right? Was it that 20% of the light gets through 20% of surface light reaches a depth of 1 meter. So that means that here's, 100% is right here. And at a depth of 1 meter, this is 20%. Okay, it's not to scale. Obviously, I probably could have drawn it anyways. But at 1 meter depth, 20% of the light remains. So what that means is that lambda equals 20%, 0.2. How much light is there going to be, at a depth of 2 meters? Well, it's going to be 20% of 20%. 20% of 20% of 100%. If we went down to 3 meters, it would be 20% of 20% of 20%, right? So 0.2 times 0.2 times 0.2. Okay, well, anyways, lambda is 0.2. You take however much light enters the meter of water, multiply it by 0.2, and that's how much light comes out the bottom of that meter of water. So we're trying to find the coefficient of extinction, and that's the name that's given to K. So we're asked to find K. Well, what's the solution? Well, of these equations, this is the one that's going to do it for us, right? We're given lambda, we're trying to find K, and here's an equation that's got nothing else in it except constants. So I'm just going to take that equation, lambda equals e to the negative k, and I'm going to solve it for k. Well, E is the base of the natural logarithms. So if I take, just give myself a little more room here, the natural logarithm of both sides, I mean, it's an equation, but if you do the same thing to both sides, it's still an equation, it's still equal. So I'm going to take the natural logarithm of both sides. Now what I've got is the natural logarithm of lambda is equal to negative k. Because natural logarithm asks the question, to what power do I raise e to get the thing you've put in the parentheses? To what power do I have to raise e to get this? Well, I raise e to the power of negative k. So that's the answer. Now this is a negative, so k must be equal to, I'm going to multiply both sides by -1, and I will get negative natural logarithm of lambda equals k. So that's my solution, because there's my formula. And now all I have to do is plug in the numbers. K is equal to negative natural logarithm of lambda. K is equal to negative natural logarithm of 4.2. K is equal to 2 natural logarithm, right, 0.2 natural logarithm. Get rid of the negative sign. Did I do that right? 0.2 natural logarithm. Get rid of the negative sign. I get an answer of 1.609437912. We started out with 1 or maybe 2 digits of precision. I'm going to say my maximum is 2, so there's my answer. Okay, did I do that right? Anybody else do this? Check my work here. You know, sometimes I push the buttons wrong when I'm talking in front of a class. All right, any questions about this? Seems right. I have a calculator. I thought somebody else might, though. Anybody else? All right, any questions? Questions? All good? Okay. Yeah. So in this class, we really have only used one equation. Okay, I'm conveniently skipping over like Simpson's index and stuff. But I mean, really, we've really only used one function, and that's the exponential function. And you use it for everything. Exponential decay of light, population growth, growth of populations, decline of the diatom population. You know, in that example we talked about earlier, if half the population is lost every day, then lambda is 0.5. And the diatom population will decrease exponentially. Of course, if they double every day, and then half of them are lost every night, 2 times a half equals 1, the population will stay the same over time. It's still exponential, but it's the trivial form of exponential where actually nothing changes, like you're multiplying by 1 all the time. So yeah, you know, we've used that all the time, so you can certainly expect an exponential calculation question in some form or another. Because there's so many forms, but it's all the same equation. Sometimes we also use linear, but I almost don't count linear because, like, you know how to do linear lines, I think. Yeah, okay. Not seeing any hands up about this. Let's move to the next question. Oofda. Describe the classical model of phosphorus cycling. In what form is the phosphorus in the water? What precipitate does it form under what conditions? What other precipitate does it stick to? In what form is it in the sediments? Why does it stay in the sediment? Why does it come out of the sediment? Well, now that we have talked about iron, I think the answer to this is pretty simple. Well, sort of. In the classical model of phosphorus cycling, it's all about chemistry. So no microbes, right? It's just chemistry. The phosphorus in the water is phosphate, and it precipitates with iron phosphate. And it precipitates under oxidizing conditions. Ferric iron phosphate forms a precipitate. It falls to the bottom. Now, phosphate can also stick to calcium carbonate floc. When the calcium and carbonate are precipitating, phosphate will stick to it. Also, iron oxyhydroxide, when that precipitates, phosphate will stick to that. That doesn't typically precipitate out in the open water. It's more likely to precipitate like in the mud where there's maybe a spring, an iron-rich spring water coming up. But it can form in the water, out in the open water, and then it would precipitate. What are the forms that phosphorus is in the sediments? Well, in the classical model, it's either there as iron phosphate or phosphate ions. If it's phosphate ions, it'll dissolve out of the sediment. If it's iron phosphate, it will stay in the sediment. And the difference is whether the sediment is oxidized, in which case the iron phosphate stays iron phosphate. The iron is in the ferric form. But if the sediment is a reducing environment, the ferric iron gets reduced to ferrous, in which case it doesn't stick to the phosphorus much at all, and the phosphorus comes out of the sediment. Okay, does that answer that question? Are there any other questions about the phosphorus cycle? Looking at my Jeffrey, looking at the participants list for hands up. Okay. Shapiro and Wright used, and if you have questions, you can ask later too. Shapiro and Wright used biomanipulation to increase the water clarity. What did they do, and how did it increase the water clarity? Well, it's top-down approach. They manipulated the food web to reduce the amount of algae. And the basic idea of this was in the classic aquatic food web, you got algae. I guess I should say phytoplankton. We're just going to talk about the planktonic food web, the pelagic food web out in the open. So phytoplankton get eaten by zooplankton, get eaten by planktivores, get eaten by piscivores. And the basic idea would be if you increase the abundance of piscivores, they're going to decrease the abundance of planktivores. If there's fewer planktivores, then there's going to be less predation on the zooplankton. So the zooplankton will increase in abundance. But if there's more zooplankton, then there's going to be less phytoplankton. So the basic idea would be to remove the fish and restock them with a good ratio, which had more piscivores and fewer planktivores, and planktivores that the piscivores can actually eat. Also, they got rid of the carp, which was stirring up the mud, which was fertilizing the phytoplankton, kind of from stirring up the mud, increasing the nutrients here. So maybe we could put the nutrients. Did it work? Yes, it worked. And the problem was, there's two things. First of all, it didn't work exactly the way they predicted. And second of all, it didn't last. And that's a problem with biomanipulation. So here's the deal. They increased the number of piscivores, right? So they added more of these. And and that was exactly what they intended. And they stocked it with less planktivores, and planktivores that were actually could be eaten by the piscivores. But then what happened is, instead of actually getting more zooplankton, they actually had about the same number of zooplankton. Number of them, but they were bigger. They were big fat Daphnia instead of a smaller Bosmina or Cereodaphnia or whatever it was. So about the same number, but they were bigger ones, big Daphnia. The big Daphnia are, 3, 4, 5 times bigger than small ones, and they eat more too, a lot more. And then the result was less phytoplankton. So they achieved the end for pretty close to the reason that they expected. But then it didn't last. And the reason it didn't last was because they didn't reduce the nutrient supply. They couldn't. It wasn't that kind of project. They couldn't reduce the nutrient supply externally or internally to the lake. And so with the phytoplankton getting eaten by the zooplankton, some phytoplankton are more edible than others. And if the zooplankton are eating all the edible algae, what you're going to end up with is inedible algae like aphanizomenon. And all of these nutrients are now getting taken up with these aphanizomenon. There's no competition because the zooplankton are eating the competition, and the zooplankton can't eat them. So you got an off the charts abundance of aphanizomenon in the very last water sample of the study at the end of the second summer. And you can go on the DNR webpage, pull up the PCA. That got water sampling from this lake. It goes back to when this study was done. And you can see that the biomanipulation, it worked briefly for a couple of years, but then it failed. It didn't last. The results didn't last. And I think the big reason it didn't last is because, this predation pressure holding down the phytoplankton took out the edible ones, but left the inedible. And unless you can reduce the nutrient supply, you're not going to really see, or you keep stocking it. Well, even then, you really have to reduce the nutrient supply to see a permanent change. I guess it was up to me. I think I would rather stock a lake with a bunch of, throw in a couple of muskie or whatever, instead of throwing in some copper sulfide to kill the algae. Like if you had to clean up a lake for a short period of time, I would definitely biomanipulate rather than use herbicide or algicide. But a lot of lakes you can't do that. So anyway. Okay, does that answer that question? Any questions about this? I like the thumbs up. You just keep giving me a thumbs up when you're happy, Desiree. I'm gonna let you speak for the class. Yeah. All right, please explain the reasoning for the separate boxes in the nitrogen transformation or sediment water interface in diagram 18.2. Now you're like, well, how important is that? Well, it is kind of, I guess. So let me just pull that up here. I think I put it in here. See if I can find it. There we go. Share this. Screen share. I think this is the diagram that we're talking about. Although I noticed that I've got it labeled as both figure 17.3 and figure 18.2. I don't really know why I've got two different numbers there, but I think this is the figure you're referring to. And why are there two different layers of boxes here in the aerobic sediment versus here, sorry, in the aerobic water versus the aerobic sediment? Okay, let's talk about what's the same, right? There's nitrate in the water, and it can get taken up by algae and turned into algae, which are particulate organic nitrogen. The algae can also take nitrogen out of the atmosphere in a process called nitrogen fixation and convert that into organic molecules and stuff inside the algae. So this is the algae. Now the algae can die and decompose, or the algae can get eaten by zooplankton, which excrete stuff. And so the living things in the water are a source of, they are themselves particulate, but they can be a source of dissolved organic nitrogen. And that dissolved organic nitrogen can be broken down further into ammonium, because it typically is like amine groups, like in amino acids. So it typically goes is first released into as ammonium. But if there's oxygen in the water, it will get oxidized into nitrate. I'm not really sure what this arrow represents, the ammonium going back into dissolved organic. I would have put an arrow from here to the algae, because algae can take up ammonium or nitrate. But I'm not willing to say that it's wrong. It's just like, I'm not quite sure why that arrow is where it is. Okay, so all of this is stuff that happens in aerobic water. All of these same things happen on the surface of the sediment. If the surface of the sediment is aerobic, like in the shallow part of a lake or the deep part of an oligotrophic lake, the sediment surface can be full of oxygen during the spring mixing or the fall mixing, right? So all of the same reactions are going to happen here. But also, because it is sediment, and we're talking about water in and among particles, like it's in the solid, it's in between the solid particles of the sediment, then we could talk about it diffusing up into the water, the movable water, or diffusing down, diffusing up, diffusing down. But also, because it's on the sediment surface, some of these ions, particularly the ammonium, can get adsorbed onto particles in the sediment, especially if there is organic matter particles or clay. Clay particles and humus, organic soil particles, are typically positively charged on the surface. So the solid components of the sediment, the ammonium in particular is likely to stick to, just by static electricity, because they're kind of negatively charged on the surface, ammonium is positive. So I would say that because there are a couple extra things, okay, maybe one extra thing that happens in the sediment, it's worth separating the water from the sediment, the aerobic sediment, and then of course the anaerobic part of the sediment. Okay, so that I think is kind of my answer to that question. Does that answer that question? Any other questions about this topic? Checking all my things. Okay. Okay. Well, then let's move on. Oop, stop share. Where'd it go? Oop. Okay, next question. Which type of algae causes red tides and bioluminescence? Okay, everybody, guess. What type of algae, what taxonomic group of algae causes red tides and bioluminescence? As soon as I get 3 answers in the chat, I will tell you the answer. So make a guess. What do you think? That's 1. I'm looking for 3 people to answer, and then I will tell you. Yeah, no. You're like, is that 2 answers? I guess I got this cat's answer counts twice, right? Huh. Yeah, no. Yes, the answer is correct. Dinoflagellates. All right, let's move on to our next question. How is the nitrogen cycle different from the phosphorus cycle? I mean, what would you say? Phosphorus cycle is simple. Nitrogen cycle is complicated. Okay. I would say nitrogen cycle is different because nitrogen has multiple forms, right? Ammonium, nitrate, nitrite, nitrogen gas, molecular nitrogen. So it has more forms. The phosphorus cycle, it's phosphate. It's always phosphate. So, in terms of like oxidation level, it's always the same. It's always phosphate. Second, a really big important difference is the nitrogen cycle has a gas phase. The atmosphere is full of nitrogen gas. Phosphorus doesn't. I would say those are the 2 biggest differences. I think there's a third one. Let me think, what's the third one? The third one is maybe the role of microbes in the nitrogen cycle. You get all these different transformations in the nitrate reduction, of nitrification, ammonification, denitrification. Every one of those different processes, nitrogen fixation, has different prokaryotes that do it, different microbes that facilitate that specific reaction. Now we saw this in the sulfur cycle, sulfur oxidizing bacteria and sulfur reducing bacteria. And those microbes control the rates in which these things happen in the real world. Like they make them go faster. But in the nitrogen cycle, it's that tenfold. There's so many different transformations, and every one of them has specialized bacteria or bacteria that specialize in doing it. So I would say those are 2 big differences. A third big difference is that nitrogen does not really have a mineral form. Phosphorus you find as iron phosphate. You also find it as calcium phosphate, and you find it involved in sedimentary rock, adsorbed to the calcium adsorbed to the calcium carbonate as it precipitated. So there's a lot of phosphorus, relatively speaking, more than enough phosphorus in rocks. There's very little nitrogen in rocks. You get a sedimentary rock and you crush it up and you let the water run over it. It's going to be a supply of phosphorus to the lake. It's going to be a bigger source of calcium and magnesium, which are the main formers of the rock. But there's always some phosphate tied up with the calcium carbonate, with the marl, the limestone. And nitrogen is just not like that. So I would say those are three big ways in which the nitrogen cycle is different from the phosphorus cycle. Explain how inorganic carbon buffers the pH of water and why removing carbon dioxide from water can cause precipitation of calcium carbonate. Well, you see that question and you got to think carbonate buffer system. So let's draw the carbonate buffer system. And you remember we read a whole chapter and there were like 20 questions about 3 pages of the textbook, which was all about one thing. It was kind of different from other chapters we've read, right? There's really just like one central concept, and that's the carbonate buffer system. All right, carbonate buffer system. CO2, the gas, dissolves in water. And gives you carbonic acid. Carbonic acid can break apart backwards into CO2 and water. And this is a pretty quick equilibrium. If you pile up too much of this, it'll shift that way. If there's too much of that, it shifts over here. I mean, it converts pretty quickly. Carbonic acid is a weak acid, which means it doesn't like hurl its protons into the water, with enthusiasm, or some kind of like nasty shout, but it does break apart. And you end up with protons and bicarbonate ion. Now, if you've got a lot of protons in the water and a lot of bicarbonate ions, then yeah, they're going to bump into each other. And this is positively charged and that's negatively charged. So if they get close to each other in the water, just by accident, they'll connect together and convert back. Of course, if there's no available protons in the water, that's not going to happen. But if there are available protons, okay, and they're never like all alone, but they'll be like loosely attached to a water molecule, that's true. But if an available proton is near, then it's going to leap off the water molecule it was hanging on to, join the bicarbonate ion and convert back. That happens pretty quick. Now, water's above absolute zero. Everything is flying around like crazy. It's a liquid. Things are like bouncing into each other, slamming off things everywhere, vibrating, rotating. There's a lot of energy going on in water. Even if to our eyes it's kind of cold, there's still a lot going on. And at any given instant, some of these bicarbonate ions will be breaking apart. And they'll break apart into protons and carbonate ions. I hope I said that correctly. Carbonate ions. And now we've got more protons over here. But, you know, if a carbonate ion gets too close to an available proton, they'll snap together and go back. So it's an equilibrium. At any given instant, some of these are breaking apart and some of them are getting together. Well, this reaction is going to happen more often if there's more protons in the water. So let's say that you throw an acid in the water, like sulfuric acid, right? Sulfuric acid carries 2 protons and it gets rid of both of them as soon as you put it in water, right? Blam. So a bunch of sulfuric acid, oh, suddenly a whole lot of extra protons. You're going to increase the concentration of protons in the water because of that. Well, what is that going to do? That means that each of these carbonate ions at any given like microsecond, nanosecond, has a higher probability of bumping into a proton because there's more of them. And that's going to increase this. I mean, there's going to be a whole lot more of this going on. And in fact, you can throw a ton of protons into the water and have them all get tied up with converting carbonate into bicarbonate. And the result is you threw sulfuric acid into the water and the pH did not change. That's a buffer. You put acid in the water and the pH didn't change. Like, how's that possible? Well, because the carbonate took up all the protons, busily converting into bicarbonate. Now, at some point, you put so much sulfuric acid into the water that all of the carbonate has been converted to bicarb. Now the pH concentration will rise. Now the proton concentration will rise and the pH drop. But if you continue to put sulfuric acid in, it stays at that particular pH. And then you can throw more and more acid in and you end up doing this. And then what happens to these? Well, if you've got too much of this in the water, it just shifts over to being CO2 and degasses. So even the carbonic acid functions as part of this buffer system. Okay, now some of these stages are faster than others. And I think that this one in particular, if I remember correctly, is kind of slow. So, or is it this one? This one is kind of slow. So this is what happens. Let's say that it's a bright sunny day and you do a ton of photosynthesis really fast. The algal community, the phytoplankton, tons of photosynthesis really, really fast. It's going to pull all this carbon dioxide out of the water, right? Consuming it with photosynthesis. If you remove the photosynthesis if you remove the carbon dioxide with a lot of photosynthesis, you remove the carbon dioxide, what's going to happen? Well, this just shifts over and releases more carbon dioxide. But that's going to reduce the amount of this stuff, which means this won't happen, but this does. These are both pretty quick, but if this one's not happening, it's all going to be that way. And that's going to reduce the amount of this in the water. So if you shift it all the way over here like this by pulling the CO2 out of the water, what you end up doing is pulling a whole lot of protons out of the water effectively pulling the protons out of the water, right? Because you're pulling all these reactions going that way. If you pull the protons out of the solution as free protons, again, they end up with the water actually, then you raise the pH. Essentially, you pull acid out of the water, you raise the pH. You raise the pH. A high pH means a low concentration of available protons. if there's a low concentration of available protons, then over here at this end, where we're focusing on the carbonate, there's not a lot of these. Now that's a problem because these positively charged ions are part of what keep these negatively charged things in solution, right? So if you remember this cartoon, here's something dissolved in water. It's negatively charged. It's surrounded by water, right? It's surrounded by water molecules. I'm not really drawing this very well, am I? Right? So being dissolved really means having a bunch of water molecules around you with the positive sides, if you're a negative ion, having the positive sides towards you. But what that means is that all of these water molecules have their negative side facing somewhere else. But there has to be a limit to that because they're gonna repel other water molecules that are facing away. Now you could keep this in solution if you had something like a positively charged ion, like the sodium. Here's some sodium over here. Sodium is positively charged, so it's going to work out perfectly. All of these water molecules that are facing this way have their negative ends could be facing sodiums, and then everybody's happy. But what if you pull all these, and skipping some steps here, if you pull all of these protons out of the water, it interferes with this process of keeping things dissolved. And the consequence is, if there is calcium in the water, which we didn't mention before because it wasn't involved, but if there is calcium in the water, and you remove all the protons, which were partially involved in the dissolution of the carbonate because of its negative charge, and I could have drawn a better picture, but anyways, you end up with these two things getting together because, you know, there's not much of that around. So now you've just got a lot of negatively charged ions in the water. And here are these other ones, which we never mentioned before because they weren't a big deal. High pH, no available protons. Suddenly this reaction is much more favored, and now you get calcium carbonate. I'm sorry, this is a double negative, isn't it? It was double negative. Calcium carbonate, and now it forms a solid and precipitates out. Yeah, okay, so that's my answer, and it's because these reactions are all not instantaneously fast. Some are slower than others, and you end up getting this calcium, the carbonate, sort of stranded without the extra protons that needs to keep everything balanced. Yeah, okay, well, there's some hand waving, but you know. Okay, so that's my explanation. All right, I don't know whether you like that or not, but there you have it. I got some more questions here, so I'm looking at the clock. Let's see how many more we can answer. If you had a question, you can raise your hand and we'll get back to it. Hey, how to calculate a confidence interval. Confidence interval is the average plus or minus a specific term. The formula for that specific term is on the reference sheet. The specific term is like the T critical value. Like, do you want a p-value of 0.05 or do you want a p-value of 0.1? You know, that determines your T critical value times the standard deviation. And the formula is on the reference sheet. Yeah, for the 95% confidence. Which of the following is not a difference between seawater and freshwater? Let's see. Seawater higher viscosity? Yes. Seawater higher density? Yes. Seawater has temperate, okay, must be temperature of maximum density farther from its freezing point. Incorrect. Seawater has lower freezing point. Correct. Therefore, this one is not true. The temperature of maximum density for seawater, 35 grams per liter of sodium chloride. Right? The temperature of maximum density for seawater is its freezing point. Yeah, it does. It does not have a maximum. It doesn't have that thing that free water does. Free water. Fresh water. That's the word I wanted. And that's pretty important. So let me just show you that graph. Let's try this one. Oh yeah. You share water. Yeah. Water. Seems nice. I spent too long creating these lovely little cartoons here. Okay, here's water. Here's the density of water versus temperature. Here's zoomed out to, oh, sorry. Spring's coming. And then, yeah, Okay, seawater. Here we go, salt water. And here's temperature, here's density. You'll notice the densities here are all higher than they were for freshwater, but also here's the freezing point of seawater. And the maximum density of seawater is right there, same temperature. This is just mind-blowing, you know, I think because it's really hard for people to learn this, even though it's like a simple graph. And I think if you didn't know anything about water before, you could learn this, you know, like that. But the problem is it kind of conflicts with things that you thought you knew about water. So that kind of interferes. But look, this is the relationship between temperature and density for seawater. Obviously, the warmer it is, the less dense it is, right? Because the warmer it is, the farther apart the molecules get from each other. And the colder it is, kind of the closer they get together. But just like a normal liquid, the maximum density is right at the point where it freezes. Okay, so that's my answer to this question. And looking at the survey to just make sure I didn't miss anything. It looks like I have answered all of the questions that were submitted to the review Q&A. And does anybody have any other questions? Looks like we're not going to get to our question about remediation. It seems to me we had sort of two of these questions. One of them was about macrophytes. You know, what are the different ways to deal with macrophytes and what are the pros and cons in each of them? And then the final question, I think it was in the phosphorus chapter, was about different methods of trying to clean up lake water. And I would say, I've talked about a couple of them, right? You can throw in something like copper sulfite and kill the algae. It's quick, kind of cheap. It works, but only works briefly. Because if the pond or the lake is eutrophic, killing the algae is just going to release their nutrients, and other algae will, you know, expand exponentially to replace them. Biomanipulation is a nice way to reduce the algae. But it has this problem of if you don't also reduce the nutrient inflow, you could just shift the algae over to an inedible form of algae because you're relying on a top-down effect. The most effective way to reduce the algae in a lake is to remove the phosphorus flowing in. And that may be hard and it may be expensive, but it's the thing that's effective. Get people in the watershed to stop using phosphorus-containing fertilizer on their lawns or fields. In Minnesota, you don't need to. It's all called calcareous rock. It's all sedimentary rock. There's plenty of phosphorus everywhere, except maybe, the boundary waters. But sewage contains a lot of available phosphate. So then that means a sewage treatment plant that does tertiary treatment. Another thing you can do is maybe there isn't that much phosphorus coming in, but it's recycling from the sediment. So a big thing that people will do, and there's a lot of lakes in Minnesota that have aerators. And the purpose of an aerator is to circulate the water so that oxygen that diffuses in at the surface gets carried down to the sediment surface. And if you can keep the sediment surface oxidizing, then you can prevent phosphorus from coming back into the water. So keeping a lake aerated in the summer to keep the sediment surface oxidized is a way of sealing the phosphorus into the sediment so it doesn't come back. You can do the same thing in the winter because if it's a shallow eutrophic lake, the bottom water may go anoxic even in the winter. But if you keep the surface open and water circulating, you can keep the bottom water and oxidizing even throughout the winter. People have done other things to try to take the phosphate out of the water and seal it in the sediment. You can fertilize the lake with ferric chloride, which I don't think is illegal, although it maybe is. But just sprinkle the lake or dribble a solution of ferric chloride throughout the lake, and then the phosphorus will bind to the iron, and then the iron phosphate precipitates out and maybe seals in the sediment. And I read a paper once from Poland where they had dumped a lot of clay dust into the lake. They had a brickyard near the pond, so I guess they had a lot of clay dust. And they just dumped a whole lot of clay dust in the lake and they formed a layer, like a centimeter thick on top of the sediment of this, this inert clay. And it sealed the sediment, preventing the phosphorus from coming back in again. I thought that was odd. I wasn't really sure how I felt about it. It seemed like pollution, but on the other hand, I don't know, it's just clay dust. So that's a solution. And people have talked about using other things like spent lime from some water softeners or water treatment plants, as the idea being put something into the lake that will seal the bottom, like a layer of something inert and inorganic. So I think those are kind of the big things to think about. And at this point, you should really be able to understand how each of those types of things would work. So if I said, explain how treating a lake with copper sulfate would clear up the water, it might be kind of hard, but that's on that list. And it's an algicide. If I said, how about, treating a lake with ferric chloride, well, that would work in a totally different way, taking the phosphorus out. Question about today's quiz. Today's quiz should be graded. They're pretty quick to grade this afternoon, I think, or it's already late in the afternoon. Let me see if there were any. What's it, quiz 10? Quiz 10, let's do a preview of it. And we can just go over it right now. I can get this correct here. Share screen. Okay, hopefully this will work. Here's today's quiz. Based on the information in this diagram, at what redox potential are you most likely to find sulfur oxidizing bacteria? Well, here's the oxidation of sulfur in this zone here. So 0. Two processes involved in the diurnally and seasonally shifting balance. This would be PS and R. And I won't get that automatically right. Okay, I should spell that out. Photosynthesis and respiration. And if I spelled it exactly like I did on the in the key, it'll automatically get it right, but many of you won't. I wouldn't, so that'll be hand graded. Based on the information in the diagram, what's most likely to be happening in lake water with a redox potential of 500 millivolts? At 500 millivolts, I'm expecting to see ammonium getting oxidized or manganese getting oxidized. What are my choices? Ammonium getting oxidized. If a lake has a ratio of C to N to P of 106 to 16 to 106 to 10 to 1, what's the most likely limiting nutrient? Well, this is not a 16 to 1 ratio. There is less nitrogen than in the Redfield ratio. Therefore, nitrogen is likely to be limiting. Does that make sense? I said that kind of fast, but there you go. Which form of nitrogen do you expect in water near the sediment, stratified eutrophic lake? The most reduced form near the sediment of a eutrophic lake. Gotta be ammonium. That is the most reduced form. Nitrate is dissolved inorganic nitrogen. Yeah, it's a molecule, but molecular nitrogen means N2, so it must be DIN. Why didn't the effort to clean up Shagawal work as expected? There is a tetrachloroethane problem in this lake, but that's not the problem. Need to know, no, nope, yeah, internal supply. Eight. As shown in the figure, this experiment with sediment from Lake Windermere. What is SRP? That's SRP is soluble reactive phosphorus. Why does it increase at 100 days? Oh, this is a written answer thing? Yeah. SRP, soluble reactive phosphorus, it's coming out of solution because the sediment is going anoxic, so the iron phosphate is dissolving. Something like that. At 80 days, the redox potential dropped below 200 millivolts, and so the iron phosphate, the iron converted to ferrous, and the iron phosphate dissolved, and the phosphate dissolved back into the water. As I said, that's not a real answer. There you go. Based on the information shown in this diagram, what is the most likely trophic status of this lake? Well, look, high ammonium concentration in the bottom water, must be anoxic down here. By golly, that sounds like a eutrophic lake. Looks like it's stratified, got high nitrate in the surface, low nitrate in the bottom. It's either eutrophic or mesotrophic. High nitrate in the surface, but maybe it's phosphate limited, so that's why there's nitrate up there. I would take those thoughts and I would convert them into an answer. Eutrophic because, something like that. And submit the quiz. And how'd I do? Oh, it's showing me my answers, but it didn't give me my score. Well, anyways, my guess is that obviously I didn't get the, anyways. Okay, so was that helpful? I'm assuming you saw that. Stop share. Here we go. Was that helpful? All right. Yeah, good, good. Glad to see some thumbs up. I hope everybody's doing okay. I know, you know, it's a really stressful time of year. Just try to stay calm, set your worries aside, just do the best you can. It's like sports psychology. Anything that's behind you is behind you right now. Don't worry about it. Last quiz, last whatever, last lab. Don't worry about anything else. Just, you know, last chance to learn a few things. Show me what you know on the exam, and then it's over. I will see you all on campus at 1 o'clock on Thursday. And yeah, that's all I got to say. If I have anything more I'm going to say about the exam, I will put it on D2L. So yeah, that's all I got to say. All right, that's it, everybody. I'll see you on Thursday. Thanks for coming to class. Couldn't have class without you.